Okay, hello, ladies and gentlemen. Welcome to another SFP London Student Chapter webinar. I hope you're all having a fantastic morning. Although I cannot see you, I'm glad you're here. Today we've got a fantastic speaker. Some of you may remember we ran a competition last year, Flashpoints, to produce the best video communicating your research topic. And the winner of this competition was Laura Schmidt, a Master's of Fire Engineering, a Master of Fire Engineering from the IMFSC. She has done a really interesting research project on the burning of timber and how to ensure auto-extinction by trying to manage char falloff. And she's going to be talking about this today. It's going to be very interesting. If you've got any questions during the talk, we've got a Q&A function in the webinar. Just post your questions there and we'll address them at the end of the talk. Otherwise, I hope you enjoy, and I'll hand over to Laura. Laura, thank you for being here.
Thank you very much for the introduction. Can you hear me? Is this all working?
It's working for me.
Perfect, easy. That's the easiest start I ever had for a presentation. So very weird to talk to people like this and not in person. So I will present my research on engineered timber and fire today, and why it is so important to understand char falloff and its impact on timber structures and fire. Thank you for organizing this event today, and thanks everyone for joining, even though I can't see you either. I've graduated from the IMFSC in 2020, and the program was an immense support for my work today. I wouldn't be where I am without the IMFSC. And I would also like to thank my supervisors, Dr. Rory Hedden and Professor Dylan Fernando. They're both at the University of Edinburgh right now, but when I started, Dylan was still at the University of Queensland. And the fire group at UQ and the composites group of UQ have supported me so much with my work. We had so many discussions that led to everything I'm going to present today. So thanks to everyone who supported me. So the reason why you're probably all here today is that engineered timber buildings are becoming more and more popular for a number of reasons. They promise to be more sustainable, they promise healthier living, they're very aesthetic. I think they can be very beautiful. In designed in the right way, they can even be cheaper. So there are many good reasons to use timber. Timber can be exposed, as in this picture here, or it can be encapsulated. Of course, it is prettier if you can see the timber, as in this picture. Architects really like that, but there are some issues with that, and that's what we're going to talk about today. Timber has been used for centuries, probably longer actually. Timber has been used for a very long time, but the way that we've designed buildings in the past is different from how we design buildings today. Concrete and steel have allowed us to build taller and taller, and we use our cities differently, we have different needs. So the question is, does timber allow the same thing? In high-rise buildings, fire safety strategies often rely on phased evacuation. So you have a fire on one floor, and then that floor is evacuated, and depending on where you are, a certain number of floors around that fire floor is also evacuated. But what happens to the rest of the building? In many fire safety strategies, we just rely on people staying put for a certain amount of time or even until the fire is out. So for that to work, the structure has to survive burnout of the fuel load. And now the question is that also possible for timber buildings? Steel and concrete are non-combustible. So these are the hazards that we are accustomed to and that we are used to designing for. But timber is combustible. And the hazards that timber poses are very different from the hazards that steel and concrete pose, exactly for that combustibility reason. And why does that matter? Different material, different challenges. For non-combustible structures, the temperature distribution throughout the structure determines the mechanical properties. And the mechanical properties determine the loss of structural integrity, which is quite predictable. So if we can estimate the fuel load, we can more or less estimate the fire, and then we can more or less predict the heat transfer into the structure. And then we know for how long the structure will remain stable, and if it will still be stable when the fire goes out. Of course, that's a gross simplification of what we actually have to do in practice, but more or less, that's the summary of it. Now, for timber, the story is a bit more complicated. The temperature distribution throughout the timber determines the pyrolysis rate. The degradation of the timber, it forms a layer of char, and it also produces combustible gases. Those combustible gases contribute to the fire. So they increase the fuel load present to burn in the compartment. Now, these processes are suddenly coupled and make everything much more complex. And that makes it harder to predict the mechanical properties and to predict the loss of structural capacity. It's no longer possible to define a period of fire resistance that is relatable to the burnout of the fuel load because the structure itself is burning. So in summary, in a timber building, the fire is coupled with the structure. And I haven't even talked about moisture yet, and it's already complex enough. I will spare you the moisture discussion today, but it also plays a role. So yes, do we have to be worried about this? The burning of timber has been studied a lot in the past and has been presented a lot in the past, more brilliantly than I could. So I will focus on the key characteristics today. Timber is a charring material. Far away from the heat, there's some section that is not pyrolyzed, that is basically unaffected by the heat. And then next, we have the pyrolysis zone between 200 and 350 degrees Celsius. This is where flammable gases are produced. And on top of that, we have a rigid carbon-rich char layer on the surface of the timber exposed to heating. This char acts as a heat shield or as a barrier for the heat, and it protects the underlying timber regions. As a result, the pyrolysis reaction can slow down until the production of gas is so low that the fire can extinguish. That is the principle of auto-extinction. Yes, I think I've said this. So the rate of depth of in-depth heat transfer is reduced, and that reduces the temperatures throughout the section thickness, and that means that the loss of structural capacity is reduced as well. But the char layer is not stable. There are different processes that can reduce its thickness and its integrity. The char reacts with the oxygen from the atmosphere, and that slowly reduces its thickness. And as is indicated in this drawing here, the timber also cracks from stresses. So then you have a higher surface area that can react with the atmosphere. And something else can happen. Pieces of the char layer can fall off, as this GIF shows. And they can be as big as you can see on the right. That's a very big piece of char and a normal-sized hand for reference. In this picture, you can see a timber compartment after flashover from a large-scale test. And you can see that there's a lot of char on the floor. And this char has fallen off from the timber ceiling here at the top. The timber ceiling was exposed. And you see how you have all these little char islands, but you also have areas where you can hopefully see a little bit. This is where the char fell off and then landed on the floor. So this is something else that takes this heat shield away that we're relying on. Engineered timber is especially susceptible to char fall-off because it consists of different layers that are glued together. And these layers can detach from each other when the timber product is heated, or when it burns, or when it experiences increased local loading. And this detaching can be caused by multiple mechanisms, adhesive failure or cohesive failure within the timber or the glue layer. And then these lamella separate. Many authors refer to this as delamination. I don't like that term because it gives the wrong impression that the entire first lamella falls off at once. But as we've seen in the pictures before, many times only small pieces of char fall off. And that's why I prefer to just call it as it is, char fall off, for sudden loss of charred material. And I just call it char loss in general to talk about oxidation, char fall off, and other mechanisms that reduce the char layer. So the loss of the char layer results in increased heat transfer to the timber structure. And we've seen before that this increases the pyrolysis rate. which then increases the fuel load, and so on. And these interacting processes can prevent autoignition. The process of char falloff is widely documented in literature and is identified as a key factor to hinder fire-safe design of timber structures. But surprisingly, there have not been any in-depth studies of char falloff or char loss and its impact. It's still perceived as very stochastic and unpredictable, and we try to start to change that. So we did a study with cross-laminated timber, as you can see here. We used columns that were 790 millimeters high and consisted of five lamella. The first lamella was 2 centimeters thick. We trimmed it down a little bit so that the first glue line would heat up earlier and the char would fall off sooner. We also loaded the sample with 39 kilonewtons. I think it's really important to account for the interactions between mechanical and thermal load. And it's also more realistic. By definition, a structure is expected to carry load. So if we don't know exactly how these processes interact, I think it's important to reproduce them as realistically as we can. And I think that's always important when you design a test setup, that you either know exactly which of the factors you're isolating, or that you reproduce what you would expect to see in the structure that you actually want to understand. We used a bending. We use bending as we think that's the worst case for the stresses in the first lamella. So we applied the load eccentrically, as is indicated in the slide, and that way the sample bent towards the radiant heat source that I'm going to show in a second. And the stresses in the first glue line, we believe that they would promote char falloff and represent the worst case. After loading the sample was exposed to heat from a radiant panel. We tested at 2 different heat fluxes, at 20 kilowatts per square meter and 50 kilowatts per square meter. Both these heat fluxes are high enough to achieve flaming of the timber sample, but the lower heat flux is below the critical value for self-extinction of timber, and the higher heat flux is above the critical value for self-extinction of the timber. So we tried to capture this range of possibilities. We didn't want to test for structural failure, so we chose a load that was lower than the expected structural capacity. And we stopped the test when the second glue line reached 100 degrees Celsius, because we wanted to observe char falloff of the first lamella only. So that way we could study the sample afterwards and learn more about the sample than if we had tested it for destruction. This was just not the purpose of our study. So here you can see the test setup. In the center you have the sample that is insulated everywhere except for the exposed surface. At the top, you can see the pin support, and at the bottom, an hydraulic actuator, or you can guess where it would be, to induce the bending load. So you can see it's shifted a bit to the back to induce bending. And then here in the front, you have the radiant panel, and depending on the distance between the radiant panel and the surface of the sample, we could control the heat flux that is received by the timber sample. And now you can also see that here at the side, I stuck a lot of thermocouple wires into the sample. As I explained before, the hazards of timber are due to 2 primary mechanisms: the loss of load-bearing section and contribution of additional fuel to the fire. And both these processes can be seen as functions of local temperature. That's why we measured these temperatures inside the timber while it was exposed to heating and while it was experiencing char falloff. To create a control group, if you will, we equipped some specimen with a thin layer of glass fiber reinforced polymer, as indicated here. So it was wrapped around the entire exposed surface of the sample and then anchored at the back with metal staples. Metal staples because we expected them to stay in place even when the sample was heated. That's also why we stapled from the back and not the front. But the polymer part indicates that we also used epoxy. You can see one of those samples here. I think then you can understand what it would look like. So the glass fiber is so thin that you can still see the timber pattern through the glass fiber. And I got a question not so long ago if the glass fiber also does something structurally. That's actually where the idea came from. Glass fiber is used to improve the structural performance of concrete and of timber. But we didn't look into that in this study. We used the glass fiber because glass fiber is inert, so it doesn't pyrolyze and it doesn't oxidize. So the glass fiber mat acted as a net and it mechanically prevented char to fall off. So this allowed for two kinds of studies, and I will present results from both of them today. So first I will talk about the char falloff that these unprotected CLT samples experienced. And next I will talk about a comparative study between these two sample types, between samples with char falloff and samples without char falloff. And that way we can start to understand the impact of char falloff on the timber. So let's look at observations from the first study of char falloff. All these unprotected CLT samples show char falloff. This sample was exposed to 20 kilowatts per square meter, and this is roughly the area that experienced char falloff. Here you can see three different samples for comparison. So all of them experienced char falloff, and you can see that the sample on the left experienced quite significant char falloff. In the middle, almost everything is gone, almost all the first layer for the first lamella of the exposed surface, while the one on the right is the one that you saw before, maybe around half of the char detached. So in theory, these samples were exposed to exactly the same conditions, the same external heat flux, the same load. They came from the same batch of CLT, and still the difference in char falloff is quite significant. I started to look at that in more detail. This is work in progress. This is why I can only show you two examples at this point. So what I looked at was where does the char fall off and in which order. So these numbers indicate when the char fell off. So here you see the first event of char fall off, the second, the third, and the white lines indicate the area that fell off at once. And you can see the left and the right again look very different. So here you have 4 char fall off events, and none of them are neighboring to each other. They're all remote. While on the right, the central part fell off, and all these events are right next to each other, as if they kind of affected each other, which is quite interesting, but it's not obviously following any pattern. We also looked at these temperature measurements that I told you about. So in this plot, every marker represents one char fall-off event, and on the y-axis you have the temperature. So this plot shows the temperature at each char fall-off event. It's scattered over quite a large range, over 600 degrees, and we have char fall-off events only at temperatures above the temperature of moisture evaporation of 100 degrees Celsius, but we had char fall-off at temperatures as low as 135 degrees Celsius, and then over 600 degrees more. So there's no clear trend in this either. And I'm showing this plot because I think that a lot of people think that temperature is the only thing that is controlling char fall-off, and that with isotherm methods it's easy to predict when the char falls off and then to design a safe building. But these isotherm methods would have to be quite conservative and at temperatures even below these 135 degrees. So I think temperature is not the only thing controlling char fall-off, and we must account for the other mechanisms, and therefore we first must understand these other mechanisms before we can continue to try and predict char fall-off. So this is only one example highlighting how complex char fall-off seems to be, and that is maybe more unpredictable than we thought it was. I also looked at the pieces of char that fell off after the test. So this is char that I selected, that I collected from the floor after the test. And you can see it's a range of shapes, a range of sizes of projected areas. And this is only a selection of pieces from one test. These are not all the pieces. In one test, we had almost 140 pieces, while before you saw we had 4 or 5 char fall-off events. So something happens in between the char detaching from the surface of the column and when we collect it at the end of the test. And I'm showing you this to highlight that a certain kind of information can certainly be gathered from the char on the floor after the end of the test. But I think it's also important to look at the char as it is falling off throughout the test. So I think we need to be careful what conclusions we draw from which moment in time and from which piece that we're analyzing. So let's move on to the comparative study. This is the control group, as I called it before. So in this set of samples with glass fiber, we experienced no char fall-off. You can see here this piece of char detached quite clearly, but the glass fiber is holding it in place. So while the first lamella is entirely charred, or it looks entirely charred, none of it has fallen off because the glass fiber mat was here, but you can see again how thin the glass fiber actually was. And this first layer of char timber clearly seems to have protected the second lamella. So that allowed for a comparative study. Here you can see the temperature evolution over time at two different depths. One relatively close to the exposed surface, 5 millimeters in depth, and the second one is 20 millimeters in depth at the first glue line. The red curves show the CLT that was unprotected, so CLT that experienced char falloff, and the blue curves represents CLT without char falloff, protected with glass fiber. And you can see that at both depths, when no char falloff occurred, when the char falloff was hindered, the temperature increase was significantly delayed. This plot looks more closely at the heating rates. This is the slope after moisture evaporation. I took the slope between 120 and 280 degrees Celsius at the first glue line. And you can see that there are 4 distinctly different heating rates between the 4 different scenarios. But on the other hand, you can see that for each scenario, the range of data is quite narrow. So I think this indicates that that when we understand when char falloff happens and what case we are actually dealing with, we can learn to, or if we learn to prevent char falloff, then we can learn to predict the response of the timber and the contribution to the fire. Maybe adjusted heating rates like the ones here could be used to design timber structures in the future. I think I should point out that this data that I presented here it looks quantitative, but we only had a limited set of samples. So I don't think that any of this data can be extrapolated to other fire scenarios or not readily. This study was intended to give qualitative conclusions and to give us an idea how big of an impact char falloff actually has. So I'm going to present some qualitative conclusions. Char falloff occurred for all CLT samples in this series of experiments that were unprotected. Char falloff strongly influenced the thermal response of the timber. So the char falloff changed the heat transfer in depth, and the faster progression of the heat transfer in depth affects the pyrolysis of the timber, as I explained before. So char falloff has an impact on the mechanical response of the fire and the mechanical response of the timber in fire, but also on the resulting fire dynamics. And this implies that the loss of the char layer directly impacts the residual structural capacity. I think that we need to develop suitable research methods to understand char falloff and its impact, because we've seen before that it does have a significant impact. And I think we need to learn one day to be able to predict it and to account for it. I think there are 3 main areas to focus on to understand why the char falls off, which mechanisms are controlling fall off, and then we can learn how to predict char falloff, and we can learn how to prevent char falloff, for example, with the glass fiber, as I showed you here, but I'm sure that there are other methods. But I think that firstly, we need to build a strong fundamental understanding of char falloff so that these mechanisms to predict or prevent char falloff can be successful and reliable. Otherwise, we would just need a huge number of tests because we're talking about real fires. So we need to look at different fire scenarios, different heating rates, different timber types, different adhesive types, different manufacturing techniques, different loading cases. I think the list is almost endless until we get significant statistical data to then reliably predict char falloff without understanding it. So I believe that unless we understand the drivers behind char falloff, we cannot move on from the scattered testing that has been done at the moment. I would really like to see that those tests being combined in a more meaningful approach, but to do that, we need to understand what is happening. I hope that I have emphasized enough how important that is to understand the impact, because fire safety strategies often rely on the structure to survive burnout in real fires. And I think that is only possible if we develop a thorough understanding, and then that will enable resilient fire safe design of timber structures in the future. Thank you very much for joining us today. If you're interested in more details, I put a few references here on the slide. I also published more details of the study in my thesis. We're also preparing 2 journal papers. One is looking more in depth on the implications for the structure and the potential of GFRP to improve the structural performance of timber and fire. And the other one analyzes and discusses the observations on char falloff more in detail. And I hope we can publish those soon so that you can read more about this. Matthew, are there any questions already?
If that's the end, thank you very much, Laura.
It's the end.
Yeah, no, that's very good. Enjoyed that. I don't think we've received any questions in the Q&A yet. Oh no, I'm completely wrong. It just didn't show up on the notification. We do have one from Colleen saying, thank you, Laura. Did you observe much char fall off that was not associated with a glue line? Yeah.
I think that's an excellent question. Yes, a bit. I can't give you an exact number because it's really difficult to connect after the end of the test which piece on the floor belongs to which char fall off event. I would say that the majority occurred at the glue line or started at the glue line, so that the entire depth of the first lamella fell off. But I did also have very small pieces falling off. So I can see on the videos of the test that sometimes it was just tiny little chunks. But I think the majority occurred at the glue line, and that is potentially because the first lamella was only 2 centimeters thick. So that's another thing that I think we have to look at. If we have a thicker first lamella, do we lose smaller pieces, or do we still lose it at the glue line?
Yeah, that would be really interesting because that sort of gives you a hint as to what the cause is, right? Or like beginning and look into these mechanisms. Thank you. This is anonymous here. Thank you, Laura, for the great presentation. I'm just wondering if there's any difference in the size of the char fall-off pieces with the different radiative heat fluxes that you use.
It would be good to know if this question refers to the char pieces found on the floor or the char islands detaching during the test. Maybe I can answer both. It is not clear for those char maps that I showed. I would say the total area of char that detaches is higher for a higher heat flux. But for those individual pieces, there's no clear trend. But for the pieces on the floor, the number of pieces on the floor was much higher for higher heat fluxes, and not in the same ratio as the area of char falloff was bigger. So the char pieces seem to break down a lot more. So it looks as if they are less intact, or they have less integrity when they detach, that they then scatter more when they fall on the floor. But I can't tell you why.
Yeah. Yeah, no, it's interesting. It makes you start thinking about all the possible hypotheses. No, those are the questions so far in the Q&A. Please post more if you've got any. But I did have some of my own questions. Looking at so, I was curious because when you were saying like that it was sort of a specific experiment, obviously not representative of a real fire and all that sort of thing, which is true. But I was just curious, in your opinion, having seen the experiments, because the GFRP thing that you're mentioning, the layer to catch stuff, looked really cool as a potential part-way solution before we understand more stuff. Do you think that would work in a real fire? And if it would, is there any sort of dangers to consider using that, the pros or cons about using it in a real situation?
I think it would work in a real fire. I would love to do a large-scale test and just wrap an entire wall in glass fiber. I think that would be awesome. We thought about that when we designed these tests. Would that actually work in a larger scenario? Because again, we wanted to make it more realistic, and we didn't want to test something that would never happen in reality. So yes, I think it would work. How well, I don't know. I think the things to keep in mind is we attach it also with the epoxy, because you need to anchor the glass fiber somehow to have a structural benefit. And that epoxy burns really quickly. And it also contributes to the fire, but the layer of adhesive that you need is very small, so I don't think it's a big negative impact. What was your second question?
Yeah, no, it was basically just if you were using it, what would you consider? Which is what you were talking about there.
Yeah.
And like, because with the epoxy as well, like, would that give it a risk of the glass falling off as well if it was like on the ceiling or something?
Yeah,
Or is
that's
that
why I think it's important to wrap it around and also attach it from the cold side. So I
Yeah.
think if I would design a real wall, I would wrap the entire wall from both sides and not just stick it on the surface. That wouldn't work.
Yeah.
I did a few small scale tests a couple of years ago, and all these different layers, they just start deforming at a different rate, and then they just all fall apart. So it has to be anchored together somehow. In the end, I used
Yeah.
a thread of glass fiber and I stitched them all together, which is a
Oh,
horrible
wow.
job. Glass fiber all over the place in the skin, it's all itchy.
Oh.
But that worked, but I don't know how well that would work if you have like a thick wall. So I think anchoring it from the other side and just hoping that it stays cold enough from the other side so that the anchor still works, I think that's important. One thing else that one other thing that I just thought of, in one of the tests, we didn't have insulation from the sides yet in the initial study, and in the cooling phase, the sample reignited again, and I think that has to do with the heat being trapped behind the glass fiber when the sample cools, and that the smoldering continues behind the glass fiber much stronger than if the glass fiber weren't there, and if the char had fallen off, it was just this smooth surface, but because the char is all there and there are these little gaps, and then the glass fibers in front of it. As soon as the fire was out, I think the oxygen gets back to the char and then the smoldering continues, and at some point it just reignited again, and it ate this big chunk of timber out of the column. So I think that's something that we also need to look into, what happens in the cooling phase after the real fire is over, and does the glass fiber then have a negative impact maybe?
Yeah. Well, I think our research group loves smoldering combustion, so any more research into smoldering combustion is great from our point of view. That's really cool. That we actually got another question come up in the chat. This is quite an easy one to answer, I think. It's for Jarl again. He says terrific presentation, which is very kind of all the question and answers. I agree. It says I might have missed it, but what led you to choose 39 kilonewtons as your loading choice in particular?
So the size of the column is the short answer. We had this test set up and this loading rig, which determined the size of the column, and the shape of the column was determined by, we didn't want it to buckle. And then we had this shape of the column predetermined, and then we calculated what would the maximum load be that this column can take. And then we subtracted a bit because we knew that we were going to heat it. And then if we heat the sample that much, how much load can it still carry? And basically then that's the load that we applied with a small safety factor, because we didn't want to break the sample so that we couldn't study it further. So we tried to apply the maximum load to keep the sample safe, and to keep us safe in the lab as well. It wasn't a structural lab, it was a fire lab. But still a significant load to bring it close enough to having an actual impact on the char fall-off. So it was kind of a trade-off between those two considerations.
Yeah, cool. It's really interesting. There's another question here from Dave. I realised, actually we've got plenty of time. We started at 9:30, didn't we? So this is good. Plenty of time for questions. Dave here is asking if you considered more than one type of adhesive. In particular, he's interested in the claim that some adhesives can prevent char fall off. If you investigated that at all?
I haven't investigated that in this study. I've heard of these char fall off proof adhesives before, of course. The adhesive in this CRT was polyurethane, and we limited the factors to one adhesive so that we could compare the samples with and without char fall off. And we use polyurethane because it is worse for char fall-off, because if you want to study something, it has to happen. But yes, I think we should look into that in the future, because if the char fall-off can be prevented with the glass fiber, then maybe we should try those things together and then we're super safe. I don't know. I think we should look into that, but we haven't done that in this study,
Yeah, no, that's you've got to limit which factors you're varying, otherwise it can be a bit.
Exactly, and I only had 2 months to do the tests.
Yeah, yeah, exactly. No, that's cool. I'm actually curious because you mentioned sort of you want to be able to predict char fall off, which obviously that sounds really interesting. I'd love to be able to do it, but sort of practical benefit does that bring to sort of fire engineering design once you're able to predict when char fall off is going to happen? How does that help with your design of timber buildings and compartments and stuff?
If you design the timber structure and you want to design it for fire, then you need to know that after the fire, after the cooling even, the structure is still standing, right? And that the people in the building are safe and that the firefighters are safe. And to do that, you need to know how much of the structure is lost. And either you can just say, well, all of the char is going to fall off and it keeps burning, but then you will never be able to have a timber building, or to have exposed timber in a timber building, or you try to learn and understand char fall off. And if you can predict it, then you can predict the structural resilience or the residual structural capacity. Because I think alternatively, you have to massively oversize your timber members. And I very briefly mentioned sustainability in the beginning. If you have to massively oversize the timber members, then I don't think that's sustainable anymore. I don't think that's good for the cost of the building. The architects would kill everyone. So I think that's why it's important to be able to do efficient designs that are still safe. I think we need to find the sweet spot in between and be able to predict char fall off.
Yeah, no, I think that's very compelling answer. But yeah, because you need to be able to, and I guess it's that other thing about like once a fire has happened, if there's been some char fall off and some remaining, you need to know at what point you need to replace stuff, right? Or like, or, you know, how much it could still take.
Yes. And it's not only the char layer that is lost, but even the underlying layers, you kind of need to know how hot it got in there, because some of the structural loss is irreversible, and that starts at temperatures like 60 degrees. So then if you can't really predict how hot the structure gets in depth, then you really don't know how much strength you have left. And then again, how much you need to replace, how much is still standing, where do you get collapse? When do you have to have the people out? How much time do you have to get the people out? I think all these questions are suddenly related. And we have just this vicious cycle of the timber contributing to the fire, getting hotter, contributing more, getting even hotter. And then at some point, everything just collapses and we can't control it anymore. Yeah,
no, it's definitely a worrying. We got another question coming in, and I think we still have time for it. So thank you very much for the presentation. In the lower range of your heat flux variation, is there any that only ignited smouldering? And so there's actually two questions. The first is, was there any that just ignited smouldering but not flaming? And then when char fall off did occur, did flaming suddenly occur after the smouldering? If the answer to the first question is yes.
The answer to the first question is yes. So they all ignited flaming, or maybe phrased differently. I defined ignition as when it started flaming.
Okay.
And because the sample was quite smooth, I don't think that there was smoldering. I don't know, maybe that's a stupid answer. So yes, all of them ignited flamingly. And then when char fall off occurred, if the sample had self-extinguished before, then the flaming reignited for all the samples where that was the case. And the rest of the samples was still burning when char fall off occurred. And then when char fall off occurred, the flames got bigger and flaming continued. So either way, after char fall off, the sample was flaming.
Yeah, cool. No, I think that's yeah. So because I think he was just wondering if like it started like pyrolyzing and then smoldering, and it wasn't until something fell off where it started flaming. But from the sound of it, that wasn't the case at all.
It was more, it ignited, it was flaming, then it self-extinguished, was maybe smoldering, then the char fell, and then it was really flaming again.
Yeah, very interesting. Well, I think that's all the questions, and you've done a fantastic job of answering them. It's been really, really enjoyable chatting to you at the end here. Yeah, is there anything else you'd like to add before we wrap up?
I think I've talked too much already. But if anyone has any further questions, I think you can easily find me on LinkedIn or maybe my email address. I'm always happy to discuss this, as you can tell. Maybe I really like these questions.
Yeah, no, fantastic. So yeah, if you do have any more questions, do feel free to get in contact with with Laura, and you're currently working for WSP, right, in Australia. So yeah.
Yes.
So thank you for coming. Yeah, the advantage of webinars, it's amazing.
Exactly, yes. And it's only 7 p.m. this time. Thank you for that. I really didn't want to present at midnight again. So 7 p.m. was great.
And so just before we go, so thank you again very much, Laura, for giving your talk. I'd just like to say, if you want more of these talks, we do them quite regularly. You can follow us on Twitter. We've got a website you can look up. If you look up the SFP London Student Chapter, you can also on that website find Laura's winning video from Flashpoints, which sort of summarizes this work into a really nice 3-minute video. So that's worth checking out, along with all our entries to last year's Flashpoints competition. Speaking of which, Flashpoints will also be running again this year. We're going to be asking for people to send in videos explaining their research. We haven't got the official announcement out yet, but that will be coming up soon. So if you're interested, start thinking about it now. That'll be coming out in the next few weeks. Otherwise, thank you very much for listening. Hope you all have a great day, and we'll see you all at the next one. Thanks, everyone.
Thanks, everyone.